Good afternoon, everyone. Welcome to my talk. It's called Crafting the Next Generation Man in the Browser Trojan. So this presentation will focus mostly on man in the browser attacks. We'll demo the Trojan that we have developed, so you'll be able to see what kind of damage one can do with it. We'll discuss defenses, and we'll propose a new approach. So my main interests are security and JavaScript. Paulo Silva, who is not here today, is a senior security researcher at JScrambler, and he also worked very hard in this project. So if you are unfamiliar with man-in-the-browser attacks, they start by a user device becoming infected, usually by some phishing campaign or any other way of social engineering attack. So the Trojan, after infecting the device, just sits quietly in the user's computer and waits for the user to go to a targeted website. Once he does that, the Trojan hooks into the browser, and it's able to freely modify the requests and responses, and also to exfiltrate sensitive information. So this is the gist of it. So man-in-the-browser Trojans, they have been around for some time. Let's do a quick dive into the history. So Zeus is considered to be the first real man-in-the-browser Trojan. It was first discovered in 2007. It only infected IE, Firefox, and both in Windows. So this Trojan, like I said, it carries a list of what we call web injects and also form grab targets. So in the picture, you can see one example of one web inject. So its structure is really easy to read. It defines an URL. And then a series of sections that define what to inject and where to inject. So in this case, the web inject is adding one extra field to a form, requesting the user to enter its ATM PIN. It was, the source code was released in 2011 by its author, and that really opened the doors for many other Trojans to evolve and upon what Zeus already did. Another Trojan I'd like to highlight is Timba. So it came 5 years later, and I'm particularly interested because it was the first one to introduce the capability of tampering with HTTP response header, in this case, the X-frame options. And you'll see in a moment why this is interesting to us. Here you can see a number of different Trojans and their capabilities. So the two most common capabilities are form grabbing and web injections. So these two are almost mandatory for any man-in-the-browser Trojan. But they have other features like keylogging, remote access, or HTTP header tampering. And of this group, only 3 are capable of spreading themselves to other machines. And this is really a feature that you see more often in more recent Trojans like ransomware. Here you can see the top 10 man-in-the-browser Trojans for the first quarter of 2017, according to research from IBM. So the top 3 are Zeus, and 2 variants, the NeverQuest and Gozi. These Trojans are responsible for a lot of financial losses and infecting thousands of users. I can give you a couple of examples. For instance, the Gozi was able to penetrate 160 devices at NASA. And for instance, Citadel alone was able to steal around $500 million. So this is really a very concerning problem that I think that we should pay more attention to. And if you think about it for a minute, it's not really enough to fix your vulnerabilities, because many in the browser attacks don't really require the application to have vulnerabilities. They can just like inject something, change the behavior of the application, and exfiltrate sensitive information and steal funds. So let's look what kind of standards we have there to defend the client side. The first one is content security policy. It allows you to restrict what scripts are executed in the page. So with it, you set policies using a special header, and you are able to define exactly what script should be loaded and where from. One important limitation that I would like to emphasize is that it doesn't apply to extensions. So this is an important limitation that will be relevant in a minute throughout the course of this presentation. Here you can see one example, very simple. It says that it must follow the same origin policy. Scripts can only be loaded from www.example.org. They should have the nonce attribute specified and match the checksum. It's also possible to have these policies in passive mode. So, and you can use the content security policy report only. It's the same syntax, but they won't block any scripts from being loaded, but they can like send back reports to your backend. The second one, HTTP public key pinning, allows you to pin a certificate to a web server in the user's browser. So there's, during a certain amount of time, that could be, for instance, 3 months. There's an interesting attack called HTTP suicide, where the server is breached by an attacker, and the attacker can generate a temporary certificate and pin the web server to that certificate for a certain amount of time. After a while, it just rotates that certificate to a new one, and the users that visited the site before, they will be blocked out of the website. And then they just contact the web application owner and tell them, hey, you want your users back? Just pay me a certain amount of ransom, and I'll give you the key, and you will be able to recover. It's a very recent type of attack. I'm not sure we ever saw such an attack, but it was presented in some conferences. This is one example. It's interesting because it also has a report URI, so it's able to report back to the web application backend. There's the strict transport security, also in a header. In fact, all of these use headers, and it allows you to enforce that the website should only be used through an SSL connection. So this is one example, very simple. Now, do you see the trend? A lot of these standards are just using headers. So someone realized that by using headers, this information gets parsed just before the body of the response being received, and as such should be secure. However, to defeat this approach, you just need to strip out the headers. And that's what man in the browser is capable of doing. So even if you could prevent this type of stripping out the headers, still these standards don't do anything to deter the man in the browser attacks. They simply can't modify the page without any blockage. But it's interesting to see that a few of these standards have implemented reporting back to the server. This is also a trend. Now, entering into the section where we talk about our Trojan. So we decided to go further, to try to see where we could go and how much damage we could do to a website. And especially, we tried to make sure that we were defeating all sorts of defenses that we already knew about. So we decided that our Trojan should remove all headers. It should offer dynamic JavaScript payloads, which is a feature that some Trojans, some man-in-the-browser Trojans already have, but we think it's very useful from an attacker standpoint, because you can react to wherever reactions the application owner is doing. And also, it should explore JavaScript code polymorphism in order to avoid detection of the malicious JavaScript. So the starting point was the Zeus source. It was the obvious starting point. But soon enough, it became very frustrating, and the development was slow. It required us, for every change to the Trojan, to recompile the binary and to infect the machines again. And it could be worse, because Zeus has a debug feature that basically disables the anti-virtualization protection, and you are able to infect a virtual machine. Otherwise, we would need to reinstall the operating system and infect so it's really slow, really frustrating experience, even though the source code is well organized. So then it hit us. Why don't we use an extension? So after thinking about it, we decided to move to a Chrome extension, because it's universal, so it works in every operating system. It's not just restricted to Windows. It's faster to develop, and of course we love JavaScript. And it was just overall easier to do as a proof of concept. And it had other advantages too. There's a new cross-browser extension standard on its way, and it's based on Chrome extensions format. So by doing this as a Chrome extension, we are on our way to support the feature standard. Also, extensions are known to have all sorts of security issues, so it was very appealing from an attacker's standpoint. Extensions are really dangerous, and let's think about it. Anyone can write them. They are usually not shy about requesting permissions. For instance, the example that you can see there, it's a weather extension, and it's basically requesting access to read and write access to all websites that you visit. So think about it. Why should it ask that many permissions? It's asking for your physical location, but that makes sense, because you want the weather, your local weather. But why should it tamper and get access to everything? So we see this all the time, all the time. Its capabilities, it's within an extension, you can inject JavaScript in web pages, modify the DOM. It's possible to execute in background, even if the browser is closed. You can send messages between extensions and add HTML as overlay. So potentially, with an extension, you can collect data, modify data, financial data, PII, passwords, tamper with destination account numbers, etc. So the extension's permission model is completely broken. It's not granular at all. So as an example, using content scripts, you can either tamper or inject scripts everywhere or none at all. So, and this is just one example. So this results in the developers of the extensions asking for everything. And you know how that ends, right? So users become desensitized. They just accept everything. It's like in mobile apps. So the requirements for our Trojan, it needed to be implemented as a Chrome extension, to be modular, because whenever you want to compile a new Trojan, you can select which features you want to include. and had the following features: header tampering, redirects to remote code execution, tamperings or web injects, form grabber to be able to access local storage and capture cookies, to do poisoning because we want to do event hijack on the client side, and take screenshots. So we were kind of ambitious. Other requirements: to be stealthy, to request the minimum permissions that we really needed. To the right, you might not be able to see very well, but it's an example of an extension that just changes the color of Facebook. Okay, I don't know why people need to do that, but I don't judge. And if you look closer, it's requesting to read and change all your data on all websites. Why all websites? Aren't you changing Facebook? You should limit it to Facebook. But this is what we see all the time. So it should be able to minimize any performance impacts and avoid antivirus and OWASP. Sorry. We also needed to implement a command and control, C2, with the following requirements. Extensions need to dynamically pull configuration from the C2. We want to have multiple distributed C2. The periodic updates must be sent to the C2 at configurable intervals. It needs to use encrypted communication, and it should be as simple as possible because we don't really care about the C2. We were just doing a POC, and we care more about the extension itself than the C2. So one of the questions we had is, can we modify headers using Chrome extensions? And we realized that since DevTools show us headers, there must be a way, right? And there is. It's called Web Request API. With it, you can access a number of different hooks that will allow you to modify headers and to modify other things at specific moments in the life cycle of requests. For instance, you can modify the headers just before they are sent out to the web server. So a few lines later, and it was done. So it was really simple. We just needed to add two listeners, request the permissions, and modify the headers or drop the headers. First, we tried to validate this visually, so by opening DevTools and just checking if the headers were still there. So that failed because they were still there, but it was working. So we realized that listeners, they follow a chain of responsibility, and DevTools is seeing the headers before our extension removing or tampering with headers. So also, we learned that by using this approach, there's a slight performance hit because it's synchronous code in a browser, but there's a safety measure, a small timeout to stop or to prevent the requests from being blocked by from extensions. Another question that we had is it possible to modify the response body? It turns out that you can't. Chrome extensions do not have access to the response body, at least yet. There's a bunch of conversation online, some threads requesting that feature, but it hasn't been implemented yet, and mostly for performance concerns. People aren't discussing if this is like a problem in terms of security, which is fascinating to me at least. But DevTools is able to modify the body, right? Everyone does it. It uses the debugger API, so we tried to do that as well. But the problem is, once you do that, since you are not DevTools, you see this. You see a bar just saying that our extension which was called YouTube Optimizer, is debugging the browser. So this is a problem, obviously, because we have the requirement to be stealthy. There is one possible workaround. Instead of changing the markup before being rendered in the browser, you can change the DOM. So you can deploy JavaScript that just changes the DOM. It's not the same thing. It's not as cool, but it works. And in order to do that, you should use dynamic content scripts because they are invisible. This is our architecture. So to the left, you can see the infected Chrome, and to the right, you can see the C2s. So the infected Chrome first connects to the C2, receives the configuration, including a list of web injects and everything. Then according to the implants that are included, it performs temperings, it performs other actions. Periodically, it sends out reports to any C2 that is available, and that information is gathered in the ELK stack, which we use to show the results. Let's go to the demos. But first, let's light up a candle to the demo gods. I hope this goes well. So first, we have the redirect. So it's really simple. It's just specify an URL and specify a target URL, the redirect. OK, so let me start the C2 code. Sorry, maybe make this bigger. OK, should be running. Now opening Chrome. Oh, actually, I don't think I remember the password. Well, I should have saved the password, right? OK, so let me see if I can. Sorry, spell. Yes. Google is your friend. Maybe let me try Bitnami. I think it's Bitnami, or user Bitnami. Let's see. OK. It was close. OK, auto refresh, 5 seconds, all right. And now I just need to open Google because it's our target. And there you go. So I opened Google, and what you see is DuckDuckGo, which was the target website. So let's see what we have here. So in Kibana, you can see that it was able to redirect from google.com to DuckDuckGo. Okay. So the second one is header tampering. In this feature, you are able to specify a number of headers and what actions you want to do. So you can capture, just collect the header, the value. You can drop it, or you can just modify the header to a specified string. Let's go there. In order to test this, I'm loading a website that tests CSP. So I'm using a browser that doesn't have the extension right now, so no tampering will occur, just to show you the difference, okay? So it's working, CSP supported, and it's blocking an image from being loaded, and another feature, which is the hash test, okay? Right. Now let's see that again, but here in the browser profile that has the extension loaded. As you can see, we just removed the CSP header, and it's not supported. You can see the blocked image, and nothing is working because we just removed the header. Let's see if Kibana, it takes a while to refresh. Auto refresh, 5 seconds, okay. As you can see, CSP, and it's just confirming basically that it was able to remove the header. Nothing really special about it. Okay. Another one, the grabber. So in this case, we are grabbing the credentials from Facebook when the user is logging in. So the configuration is really simple. You just need to specify an URL and which fields you want to collect, or leave it blank and it will basically collect all the fields. So open Facebook. Okay. So Pedro at OWASP.org. This is not my email, by the way. And as password, I'm going to write my password. Surprise. Okay, so this account doesn't really exist, but I want to test if the extension was able to grab the credentials. Okay, so, and by the way, the grabber grabs data from post messages and AJAX messages. So, and Facebook uses both. So let me see, login attempts, let me see the details. Okay. Pedro at OWASP.org, and my password. Really simple. Okay. I have a ton of demos. Everything, it has everything to go wrong. Now the screenshot. I just need to specify an URL and enable the screenshot. It's really easy again. So what I'm doing is I'm grabbing a screenshot from Google Mail, okay, which is interesting. Okay, let's do it. Chrome extension. Okay, open Gmail. This is a new account. I wouldn't show my own personal email, sorry. And there you go. You have a sample email, and it seems that I sent my some password in clear text using Gmail. I should have known better. And let's go see what we have here. Screenshot. This part is not really convenient because it stores a data URI in Kibana. So, like I said, we weren't concerned with the presentation aspect of it. So let me just select this whole thing. I need to edit. And remove this part. Incidentally, I need to use Firefox because I cannot paste this amount of data in Google Chrome. There you go. So this is the screenshot, and I can see the passwords from here. And I could take as many screenshots as I like, and sensitive information might be leaked. Okay. DOM tampering. So with here, I need to specify JavaScript that will be injected into the context of the web page using dynamic content scripts. And basically, by running that JavaScript, it will modify the DOM. And for this, I'm using a dummy virtual bank application that I will show you. So I need to start the new application. Virtual banking. Okay, just start the web server. Sorry. Okay, so it's available in this address. And show extension. Okay. And I have here. Okay. There you go. So this is the virtual bank. And now let's see what we get if we load the same website using a profile that doesn't have the extension. You see the difference? So the left one is showing a banner inviting the user to download the mobile app. If you look closely, no, I can see the links, but it's pointing to an attacker-controlled server, and the user could easily be fooled by this. Really simple. Okay. And here I have the event of the JavaScript that was executed. Okay. So one question, what was the strategy that we used to infect users? And the answer is we didn't. We don't want to release this in the wild. So everything that we are talking here is hypothetical, of course. So right now, the extension needs to be loaded using side loading. So it's not in Chrome Web Store, obviously. And possible vehicles for infecting a user is the traditional phishing emails, having malicious macros that basically load the extension. This is not hard to do. You could have drive-by websites that invite you to download the extension. I'm seeing some examples occurring. Or you could just do a pull request to an open source Chrome extension that sits on GitHub. And maybe the guy managing the project will be caught off guard. So to avoid detection by the user, we selected an unsuspecting title and icon, and we requested the minimum permissions. To avoid detection by the antiviruses, we used polymorphic obfuscated JavaScript, and I'll talk to you about that a little more in a minute. And on the wire, we just encrypt everything. So polymorphic JavaScript was used to avoid blacklisting. You can see two samples of JavaScript, of protected JavaScript. So potentially, each user can have its own version, and this can be served dynamically. And antiviruses are really bad at detecting malicious JavaScript. So if you do this, there's no way they can be effective against all threats. So and using polymorphism gives the extension some more resilience against tampering. So if there's other JavaScript trying to detect the extension code or what it does to the web page, it will be harder. So let's collect our thoughts a little bit. What does this all mean? So current standards, they don't offer protection against man in the browser. Header-based defense can be disabled by removing the headers. Obviously, it seems easy, even though we haven't tested, but it seems easy to infect users using this Trojan. And antiviruses are ineffective. So we believe it's a valid vehicle to perform man-in-the-browser attacks. It's simpler, faster to do, and I believe it can replace traditional man-in-the-browser Trojans. So what else is out there? Let's think about that for a minute. For instance, other solutions, not standards that you can find, device fingerprinting and geolocation, they don't work because the user is using its device, its browser, and probably accessing the internet using its usual location. Fraud monitoring, it might work because it's specific to the business. But Trojans can be subtle. They can let's the virtual banking example. They can modify the destination account number and not change anything else. So how can we be sure, as a bank, how can we be sure that that was not the intended destination account number? So it can fail. Bot detection and behavior-based detection, they fail too, because it's the user commanding the navigation. So we propose a different approach, application real-time monitoring. It follows the observable pattern. Basically, we continuously monitor for DOM modifications, for tampering to native APIs, and tampering to events. It follows a whitelisting approach, because we learned from antiviruses that you cannot possibly recognize everything that they will shoot at you. So it's able to detect anything that shouldn't be there, and we use machine learning for tackling the false positives. So it sends out real-time notifications, and those notifications can trigger reactions, automated reactions from the web application. It allows for self-healing. So if in some cases we can remove the injections. But all of this, to be able to work, it must be delivered with code protection. Otherwise, the code of the solution will be very easy to tamper as well. And for that, we use client-side WASP. So the final demo. Okay. So I'm using, again, the virtual bank application, but first I need to enable the solution. I just need to add one line of code. It's easy. It's commented out. I just need to remove the comments and start the thing again. Okay. Now, it's putting this side to side. This is the dashboard, completely clean. Okay. And let me open the virtual bank. So have you seen it? The banner was removed automatically after a split second. And we can see to the right that we were able to detect the tampering and the correct detection. So you can see the injection in red, and we were able to successfully remove it. And another interesting aspect is that you can see the whole application in context. So you can really see the code that the user is seeing. Let's continue, log in. Do a transaction. And even before confirming the transaction, I'm seeing new threats coming in. Let's see what it caught. So it turns out that the extension was able to change the onSubmit function to the one that you see on the right. And it is basically collecting the destination account number, replacing by its own using hidden fields, and removing the original fields. Okay, this is all automatically when you submit the function, not before, just when you submit the form. Obviously, when you use your online banking, you are not checking the code, right? So you don't open the code and let's see if it's has been tampered or not. So this will fool anyone, even a specialist. So more threats, and basically what it's doing is replacing the destination account number of the attacker, because that's what the bank received, right? By the destination account number that the user was expecting. And this is needed in order for the user to don't suspect anything. So as you can see on the right, we can see that an element was tampered and John Mark was placed in that field. So wrapping up, so modern man-in-the-browser Trojans are able to compromise web applications. They can inject arbitrary codes, modify events, do API poisoning. Attackers can collect information, can trick the user into doing things he's not aware of, and perform all sorts of fraud in the web applications. They are able to completely bypass current application security defenses, and most techniques outside the standards won't detect the activity of these Trojans. So we basically deployed a new vehicle for delivering man-in-the-browser attacks, and also we proposed a new approach for detecting the activity of man-in-the-browser attacks. So we argue that in order to tackle this, you need to continuously monitor what happens on the client side and react in real time, both by removing the injections or by sending out notifications to the backend. And here we are just following the trend of the current standards, because CSP does it, HPKP does it as well. And really it's also interesting that you have built-in reporting capabilities inside the apps and in an automated fashion. So reporting shouldn't be implemented, in our opinion, by developers, because they may not know, and they usually don't know what is malicious, and they shouldn't be implementing this reporting. So this should be done automatically. So that's all I had. Thank you. I'll take some questions if you have.
Excuse me. Oh, I think it is on. Great.
He's on. How easy is to infect the browser and kind of like mislead the user that to install that extension? I think it's pretty difficult for most of the experienced people, but I'm not sure about the public.
So it's really easy, because the first suggestion that we are doing is just to use the traditional approach, just to use phishing campaigns, send out malicious attachments, and some users will be infected. And history has been proving that this is still effective, and the attacker doesn't really care who gets infected, All he knows is that a percentage of the users of a target website will be infected. And this we know for sure.
So this phishing email that you mentioned, will that trigger installing the extension in that location where the extensions of the Chrome, or it will actually launch the Chrome and the user will have to accept to install that extension?
It depends. It can go both ways. So you can place the extension.
What is the most effective way to infect?
I believe it's by placing the extension in the folder. There's a protection against that, but you can but because you are controlling the operating system, you can also try to remove that protection and install the files in the user's profile.
Okay. And do you have any idea what percentage of the mass population normally can be tricked that way? Is it small percentage or big percentage?
I mean, there's a small percentage that can be infected, but after being infected, I think everyone can be tricked because it's really invisible, right? Mm-hmm. Unless you suspect that some injection something that shouldn't be there, unless you suspect something is off, you won't really discover that you have been infected.
And you also show these icons that appear as extensions in the Chrome. Wouldn't that make the extension visible? The person will notice,
yes.
Oh, there's something that it's new on the screen.
Potentially, yeah. So the user can suspect that they haven't installed that specific extension. But then again, remember that it's the same people that were infected by opening like phishing emails. So it's not the kind of technical person that will like, hey, I haven't installed this extension. In fact, that person may not even know what is an extension at all.
And I remember also Chrome, usually it does checks all these extensions and verifies their signature and validates whether they're coming from the official Chrome repository for extensions, and can detect whether it's just site loaded from the operational system. How you can deal with that?
There's no protection against that. It's perfectly legal to do side loading of an extension.
But Chrome will notify you as a user. It will tell you.
It will not. So I've shown you that it doesn't notify the user. There's no mechanism for warning the user, like in an effective way, that some malicious extension is running.
Maybe something is missing because I have done this loading from directory of. I've written my own plugin extension, and Chrome immediately tells me when I'm running. It does recognize that I have.
So maybe I am missing something because we during our development it never occurred to us.
Okay. Okay. Thank you.
Thank you.
It was an excellent presentation. Thank you.
Thank you.
This is interesting from a browser security perspective, and I work for Mozilla, not directly on Firefox, but we do a lot of like how to keep web extensions somewhat secure. And one of the problems we have is that we have so many of them, we essentially cannot review all of them. So we know that some of them are going to go through. Maybe we'll review them once, but then the next update could be malicious and they could become the kind of malware you're describing. And it's very difficult from our perspective to essentially, blacklist to detect that an extension has become malicious. But I was wondering if you had any ideas as to what the browser should do or could do to protect users against these kind of extensions that became malicious and are starting to take screenshots or these sort of things.
So first of all, you cannot do anything if it's being sideloaded, I think, unless it was referred here, unless the browser is checking for sideloaded extensions and trying to pick up malicious characteristics in the extension and reporting back. So that could be effective, potentially. But then again, you have the same problem that you have when developers submit the extension to the Chrome store, to the add-on store, because I'm guessing that you are doing static analysis. If you are doing static analysis, it's pretty hard to detect what is malicious, because there's lots of ways to completely hide malicious behavior, because JavaScript allows that.
Yeah, we pretty much gave up on that. Like this is too easy to escape.
Yes, it's too easy to escape. JavaScript is too dynamic. You could potentially use dynamic approach, have a way to launch every extension in a controlled environment and just monitor the extension for loading extra codes and even use a modified browser that is able to somehow pick up on malicious behavior. Not really the malicious code, but malicious behavior, like loading a third-party script that wasn't in the manifest, something like that.
Thank you.
So regarding a comment about like removing the report only for CSP, I'm not sure that's a great idea, because that's what makes it easy for developers to roll out such headers without breaking their sites. Of course, it's not great to use that as a primary mode of security, but I don't think removing that is going to solve the issue there.
What do you mean, removing?
The reporting only for CSP?
Removing the reporting?
Yeah.
No, what we recommend is that you have reporting. We don't recommend you to disable CSP. We just talked about that as a possibility, because you should use CSP in active mode. But it's interesting, the reporting capabilities.
Okay, got it. Yeah.
So just setting aside other malicious things the extensions can do, if you're just focusing on like changing DOM of the victim page, does it change anything if I load the CSP in a meta tag? Because you mentioned the DOM can be actually changed, thus the CSP policy could be also changed. And then maybe after that, even if it's possible now, wouldn't this be a good fix for browsers to sort of prohibit extensions of changing the meta tag with CSP policy dynamically from the extension?
So your first question is, the CSP blocking dynamic scripts from the extension, right?
Well, CSP can be loaded either in headers or in a meta tag, right?
Yeah.
You said that in headers, this can clearly be stripped away, and then the extension can actually do anything because the CSP policy is not active. If I load the CSP policy in a meta tag, you said the response cannot be edited. So the first initialization of DOM, it's actually the one with CSP. Then I guess the extension needs to change the CSP dynamically. And if this was prohibited, then this would at least solve the issue with extension changing a DOM.
Yes, you're right. That's a really good observation. So loading the CSP through meta headers, in this case, in our extension, it would actually run the CSP. And because we don't have access to the body right now, only indirect access to the body, the meta headers would be executed before we were able to remove those tags. And the other thing is the CSP currently doesn't restrict dynamic content scripts in extensions. So if somehow the extension standard decides that CSP should in fact control whatever is executed through an extension, it could be effective.
Yeah, thanks.